Welcome back. We are going to calculate the probability of loss when there are a lot of customers, independent customers. So always the first thing you have to do is to calculate the expectation and standard deviation of the average. To do that, we already calculated the mean and the standard deviation of a single outcome. So it's easy now. The mean is the same. Remember, the mean does not depend on the sample size. So even if the sample size increased, has no effect. It has no effect on the expectation of the average. But the standard deviation does change depending on the sample size. So the denominator is the square root of the sample size, which is now square root of 10,000 equals like 10, like 100. So 900 over 100 equals 9. So standard deviation is only 9 now. It was 90 in the previous case where there are 100 customers. And therefore, we have mean and standard deviation. So you have the parameters for the normal distribution. And then standardize the probability. The method is the same, but we use a different standard deviation because it's different now. The mean is the same, but standard deviation is different. And then if you calculate this side, it is now minus 22. Minus 22. If you put minus 22 into the CDF of the standard normal distribution, you will get 0%. Of course, when you extend the decimal places, there might be non-zero number, maybe somewhere here. I don't know. It's extremely small probability. So we usually assume that like plus minus 4 contains 99.999% of the whole probability for the standard normal distribution. So minus 22 plus minus 4 contains almost every all probability. So minus 22 is super extreme case, which should almost never happen. So anyhow, it's 0%. Unless when you round at the third decimal place, it's 0. So this is the power of the risk pooling. This is how insurance companies work. And simply speaking, as the sample size increases, the risk disappears. This is the law of large number. And we just have shown the mathematics behind it. And this is how exactly insurance companies manage their risk and make profit. So they try to pool as many customers as possible, so that kind of the policy holders are insuring each other, right? So I'm not saying insurance is useless. It's worth, and just this is the mechanism, statistical mechanism behind it. Okay, that was I hope it was an interesting example, and I guess you are going to learn something similar in microeconomics or game theory or somewhere. Okay. And another topic I have to mention in this chapter. By the way, this chapter will be short, so maybe it's much shorter than other chapters, but instead later chapters might be longer than usual. So it's a good time to change up. Anyhow, I am going to compare the sampling distribution theory with the binomial distribution theory. So there are some commonalities between them, because in the binomial distribution chapter, in chapter 5, we assume there are a few assumptions, and two of the key assumptions are these. You have to repeat binary experiments for n times. You have to have n experiments. That's how you get a binomial distribution. And also they have to be statistically independent of each other. Then given n number of trials, binary trials, you count number of success among them. That's the binomial distribution. So if you define x, variable x, as the variable for a single experiment, binary experiment, then when you sum them, it is a binomial distribution. So remember, y is the number of the count of successes which equals the sum of zeros and ones. So success is 1, failure is 0. So when you sum all these numbers, zeros and ones, then you are going to get the count of success. It follows a binomial distribution. And the average of x is defined in this way as usual. Sum divided by the sample size. So by the sampling distribution theory, by the central limit theorem, we know that its distribution converges to a normal distribution. So basically both are the same thing. The only difference is we divide by n. We divide the summation by n, and that's one difference. And another difference is that the binomial distribution is not an approximation. It is an exact distribution, exact probability distribution. There is no error at all as long as the assumptions are satisfied. But the normal distribution is an approximation because it just says it converges to a normal distribution. It means it's getting closer to normal distribution, but still there may be some approximation error as long as the sample size is finite. If the sample size converges to the infinity, then it is perfectly normal, but we cannot get to the infinity, so then there will be approximation error. And another point I wanted to say here is that in many applications, in some applications, the number of successes matter. They are important. In some cases, they are important. But in other cases, I don't care the number, but I care more about the average. So average is the probability. Remember, in binary distribution chapter, I explained that the average has to be interpreted as the probability of success. So in many examples, we are interested in the probability of something instead of how many people do that. For example, political poll, like election, like survey for the presidential election. I don't know how many people surveyed are in support for Donald Trump, the president, or Biden. What I'm interested in is their relative proportions. So not the absolute number count, but the proportion. So in some applications, the averages can be more useful than the count y. Excuse me, but they are closely related. So we are going to compare them and how they are different. So we will. I'm going to consider this example from the next video. This is the last example of this slide. So I'm going to stop the video here and continue in the next one. See you.